this is Introductory Nuclear Physics, primarily for undergraduate students, and it is based on the Crane's book. I will give the details. In this, I have planned the course in this manner that we will discuss initially the history of atom, then quantities and units in nuclear physics. Then we'll talk about radiations and atoms and atomic models. Later on, we will study binding energies and energy levels and how to compute binding energies for various materials. Then we'll focus on nucleus and its terminologies and notations. And then we will discuss models, nuclear models, and the basic ideas of nuclear force. In this regard, nuclear emissions and binding energies again become important, and we will talk more about the decays, beta decay, alpha decay, gamma decay, and related various balances. Then we will come to define radioactivity and its related activity and definitions and exponential decay laws and specific activity and decay of mixed radionuclide samples. Then I'm going to talk about the parent and daughter decays and Batman equations. My focus will be on the circular equilibrium. Then we will discuss the fission and fusion reactions and the fission-based nuclear reactors and their principles. And in this regard, we will further go on discussing the neutrons, how the neutron was discovered, what are the properties, and how to develop a neutron source. Then I'm going to talk about the accelerators, principles of accelerators, and we will also discuss the photonuclear activations. These are really desired when people want to know what's happening in the nuclear medicine. And we will talk about the equations of radionuclide productions and radioisotope generators that are now popular among the various medical centers around the world, and people are using nuclear physics applications there. At the end, I will go through the fusion reaction in detail and the possibility of developing a fusion reactor system. So we move further with the history, a brief history of atom today. In this lecture, this is the first lecture, we'll talk about the atom. First few ideas are due to Greeks. They thought that the matter can be subdivided and into small particles. We can go as low as possible, and then it becomes no more dividable. We cannot further break it. And once it is not breakable, they called it atomos. This atomos, that is, we cannot cut it further, was written as atomos initially in Greek transcripts, and now we know this as an atom, which is distinct in shape, distinct in sizes, distinct with the materials. First few ideas that were really key, we come to know are through Aristotle's opinions. People thought him to be a teacher of teachers, and for more than 2,000 years, nobody did anything to explore further beyond the Aristotle's ideas. In English, written in 1800s, John Dalton came up with the experiments on various chemicals and showed that matter indeed seems to be based on elementary lumps or some very, very tiny particles, and we can term them atoms, he said. He said that all matter is basically based on tiny particles, and atoms are indestructible, not changeable, and elements are really identifiable through their masses of atoms. When elements react with each other, the atoms combine in simple and whole number ratios, and the theory was termed as John Dalton's theory for chemical reactions. Clearly, this had better visibility, and people started liking it. Indivisible particles called atoms became popular, and they were then identified in compositions, and some properties of materials were identified with the atoms, and people started terming and defining names. Atom can neither be created nor destroyed was the idea behind Dalton's atomic theory. Atom of different elements can unite together in simple whole number ratios, and atom can combine in more than one ratio to form several different types of compounds. This idea led to the law of multiple proportion in chemistry, and now it is a sort of law which provides a balance in the chemical reactions. Chemical reactions involve rearrangement of atoms. That was the Dalton's idea. At Cambridge University, British were working on the properties of atom, and few strange rays were in the discovery process. When J.J. Thomson announced that he has discovered the existence of charged particles, he termed them electrons, and he published a paper on these observations that both cathode rays are electrons, and concluded that they are the negatively charged particles with certain mass. And then he started working on measuring the mass and the charge, or the ratio of charge to mass. The electron then, now we know very well that it is a negatively charged particle, which is very, very small, and its mass is smaller than the hydrogen atom, roughly about 2,000 times smaller as compared to hydrogen atom. He also told that the opposite charged particle resides with the atom. So electron and the oppositely charged, he termed proton, coexist in atom, and they actually balance, and the overall charge on atom is 0. Here you can see the J.J. Thomson's apparatus, and J.J. Thomson observing and pushing the key to initiate the process of ionization in the development of the cathode rays. This is the original apparatus, and it's a schematic diagram. Here you can see the anodes, the positively charged with the help of a battery. They are having a cylindrical shape, and the electrons that are emitted from the cathode plate go through this cylinder, and from a hole they emerge out, and they are deflected by the positive and negative plates, and then they are thrown at the surface of the tube, and the surface of the tube has a zinc sulfide plate, and dropping there, they start emitting light, which is greenish, bluish light, and that's how we come to know that the electron beam has hit the plate. The cathode rays electrons have properties that they can cause visible light emission from zinc sulfide screen. They can travel in straight line. They can heat if they are stopped. They have momentum. They are deflected towards positive plates, and electric field influence them. Magnetic field also influence them. They start moving in circle when they feel the magnetic lines, and they are deflected perpendicularly to the magnetic field in a direction because they are negatively charged, so they are expected to be deflected. These were the original few properties published. Now we know that E by M value of these cathode rays is 1.7588 into 10 to the power 11 coulombs per kg. And now we know very well that atom can be split. We can divide atom. Atom is actually composed of electrons that were removed from the atoms, and the rest of the atom is positively charged, and the charge is same as that of the electron. So in these experiments, the mass of the electron was shown as less than 1,000 times the mass of the hydrogen. And eventually Millikan measured the mass of electron as 9.1 into 10 to the power minus 31 kg. This minus 31 is very important. It tells us how small the mass is. And it's nearly zero, but it was measured, and that's how we come to know that how precise in physics we can measure things. When we see the early atomic ideas, the first idea about the atom is that there is evidence in the Brownian motion of molecules in a gas, that the gas molecules are moving around, and the tiny molecules show that they have some smaller structures. Now we know that there is an internal structure of atoms. Now we know that there is a discovery of radioactivity in chemical reactions. Now we know very well that there is a nucleus. However, the earlier models did not have this privilege, and people had only knowledge of the electromagnetic radiations. That is, they knew the light. The light-related properties were known, for example, light emission, light absorption, the visible light spectrum, the infrared and ultraviolet spectrum, and the characteristics of spectrums of different elements were known well before the birth of atomic theory. However, people used to heat the materials, and heated materials used to emit visible light. And the visible light used to be thrown in front of a prism or prism-like material, and people used to find out the spectrum. So there were books on spectrum. There were ways in which the atoms were combined with each other, and people never knew that the atoms are involved. They knew that the chemical reactions do occur. Now we see the X-rays, the electron, the radioactivity, the birth of new particles. So we need to learn about the internal structure. We need to understand the properties of the individual part of the atom, and we would soon see how these parts act together to make the system operate. So it is just like an auto transmission, in which we first learn about the nuts, bolts, and gears, and then we study about the transmission. Here we would like to see that we need some way to observe these things, and people generally use their fingers to examine the transmission of a automobile or a mechanical watch, but fingers become too large to study a variation of small components of a watch. So you need sight, you need light Then light starts showing you how the interactions occur. The wavelength of light becomes important, and we know that the wavelength of visible light is of the order of 500 nanometers, and it is much smaller than the parts of a watch, so the parts of watch can be seen. Smaller the system, the smaller this probe we need, and smaller the system goes further, the smaller the probe should be. So atomic models need some image or a mental image, and we must have experiments through which we can see what is atom. Before 20th century, the properties of the atom basically were thought to be that atom is very, very small. We cannot see atom. Atoms are stable. There are forces that are pulling apart the atoms, but there are forces that are keeping the atoms. Therefore, atoms are there and stable. Atoms are not really going away. Atoms are containing no charge at all, but they contain negatively charged electrons, J.J. Thomson had told us. So there must be some charge on the rest of the atom, and it is, if it is with the Z electrons, then it must contain plus Z electron charge. Atom emit and absorb radiations or light, but they do not always emit and absorb light of the same wavelength. They can have different wavelengths. The atoms have certain character, and their character can be identified with the help of this light, which we see. So early model of J.J. Thomson was something called Plum pudding model, in which electrons were distributed throughout the atom, like raisins in the plum pudding. If we can see the plum pudding, the raisins inside distributed, part of it is shown here. So atom, something like this, a uniform distributed thing, and in which these electrons were like raisins, and we see that these small particles were distributed. So this atom model was having a uniform charge, a positive charge, and a uniform distribution of negative charge. And so overall, the atom was neutral, and you take a part of atom, it is still neutral because of the uniform distribution of negative and positive. J.J. Thomson had shown that the electrons are coming from atom, therefore they are part of the atom, and they are negative charged, so the rest of the atom is a spherical volume with a positive charge. His atomic model was taken very seriously, and nobody challenged it earlier except his students. J.J. Thomson said that his model had the basic idea that electrons can repel each other because of the same charge, but they will remain attracted towards positive charge, and therefore the stable equilibrium will happen. But oscillations of electrons, if the electron starts moving around, then they are going to produce electromagnetic rays. We know from the classical electricity and magnetism, moving charges produce light. So there must be visible light. So oscillation of electrons will produce visible light, and it will be a continuous light, and it will then finish the atom. So the drawback was that atom spectrum of hydrogen atom particularly cannot be predicted. The difficulty of emission and absorption of light is there. The failure is how to describe the scattered charged particles of atom, how to know where the electron is residing, which electron is residing where. These were basic drawbacks, but J.J. Thomson's initial model was a good hit. Then experiments were showing few new things. For example, a laboratory scattering experiment showed that the small angle deflections were not seen, which means that the most of the particles will pass through the atom. So it is a very fluffy cake. But experiments that were performed by Geiger and Marsden, they showed that there is alpha particle scattering for greater than 90 degrees, and the probability is high. And this was repeated again and again, and they saw that there is a particle scattering coming from the atom. So atom is not really the fluffy cake. There is some hard thing in it. This result led Rutherford to propose another atomic model. The gold foil experiment, it is termed. There is a thin gold foil I've shown here in a bit larger size, but it is very, very thin. So alpha particle scattering at the angle larger than 90 degrees is a problem. Why particles are not really passing through, they come back or try to deflect back. So there is a hard thing there inside the atom. It is not very, very sponge-like. Rutherford was a student of J.J. Thomson and doing master degree at that time. And the gold foil experiment was done with the Geiger and Marsden, their PhD students, in 1911. And actually experiment was done, and the explanation of experiment was really the mess. Rutherford reasoned that if the Thomson model is correct, then mass of the atom was spread throughout the atom like a sponge cake. But if we shot high-speed alpha particles, then alpha particles should go through it with little deflection. But alpha particles that were helium atoms, they were used as a probe. They started coming back also. Few of them started coming back. The beam was directed at gold, very thin gold, and zinc sulfide screen was placed at different angles. And they watched the flashes, and they claim that when they used to come out of the laboratory, they used to see the flickers of light everywhere. In broad daylight, they can see the flickers. They used to work on microscope in a dark room with the alpha source, and used to have a zinc sulfide screen from where the light will come out as a flicker, and they will count it as a 1, 2, 3 count for that particular angle. This discovery that few of them are coming back, the alpha particles coming back from the gold foil, it is something like bullets that are going through a haystack and still facing some brick inside. So majority of the bullets are passing through the haystack, but few of them are stuck with the brick. So what to do? This was the result. It is not a uniform distribution. It is something which is shown here, that something very hard inside. So Rutherford's experiment was changing the ideas of the atomic model, that majority of the atom is not a uniform distribution of charge. The charge is really lumped at the center. The positive charge is lumped at the center, and the rest of the electrons are outside this center. And when you throw the alpha particles, majority passes through, but few of them come back. Here I show the modern apparatus of Geiger and Marsden and Rutherford, the scattered particles in thin gold foil and the alpha source. By the way, this alpha source was borrowed from the Curies. At that time, it was the only source available in France, and Curie's home had this source, and they borrowed this source to do this experiment for summer. And for 3 months, they used this source to do this experiment. The observation was very clear. Most of the alpha particles are passing through, and very small alpha particles are getting deflected at small angles, and they are really important. And a very small deflection at a very large angle is also occurring, and this is something like coming back. The alpha particles come back. So they can come back only if they are going to hit something very hard. So hypothesis was that atoms consist of the positive subcomponents, and it is concentrated, and they termed it a nucleus. So Rutherford's conclusion was that most of the volume of the atom is empty. It is empty space. It does not carry any charge. And there is a nucleus inside. It is positively charged. Most of the mass of the atom and the positive charge is located in this very small dense region, and the nucleus is its name. Electrons are revolving around the nucleus in orbits, and each electron has a particular orbit. The picture is not to the scale. It is, as you can see, if I try to imagine, let me call 1 centimeter of our own scale equal to the size of the nucleus. This small size, which we now know, it is about 10 to the power minus 13 centimeters, or 10 to the power minus 15 centimeters femtometer. Then the first electron which is going to orbit is at 10 to the power minus 8 centimeters. Now, these are so small numbers that we really cannot imagine, but I can convert 10 to the power minus 8 into my scale of 1 centimeter by dividing by 10 to the power minus 13, and I get a number of 10 to the power 5 centimeters on my scale. So if I convert it, I get a 1 kilometer. So if nucleus is the size of 1 centimeter, then the first electron, which is orbiting around it, is at 1 kilometer away from it. So it's a horse in a racecourse ground, which is bound to a nucleus, and it is revolving around the nucleus in a 1 kilometer radius circle. Horse so far away. So in between space of 1 kilometer is all empty, nothing inside. The nucleus is 1 centimeter. The distance between the nucleus and the electron is 1 kilometer. So you can imagine the atom. It's a very, very strange atom predicted, and a model given by Rutherford and his colleagues. And J.J. Thomson never felt happier about this, as he knew that the explanation to the experiments was very clear. The Rutherford's atomic model became very famous. It is sun-like model, in which there is a center and a sun, and there is Earth, and there are other planets. And this model is basically a miniature solar system. The Geiger, Marsden, and Rutherford's rejected and tested Pudding's model, and converted that model into a miniature solar model. And that solar model was the most popular model. Alpha particles deflection also was again and again proved to be very fruitful. Now we very well know that the Rutherford scattering became the scattering experimentation for all the times to come. Now, whenever we want to discover anything new inside the atom, we perform the scattering experiments. Now we have the finer and ultra finer particles to do the scattering, and that's how this probe is becoming small and small and small. However, the solar system model suggested by Rutherford had one small drawback. It has never explained the stability of atom. It never told us why the moving electrons are not radiating energy and why they are not killing themselves by collapsing into the nucleus. Why don't they collapse? Why don't they emit the continuous radiation? Why they emit a discrete one by one light? Why they have different types of lights? Nobody could tell from the Rutherford's model that the visible spectrum of hydrogen is really experimental, and is there a theoretical explanation for such kind of radiation emission? The continuous range is predicted by the all electromagnetic theories, but we see the discrete spectrum. So Rutherford model needed further clarities, modifications, or further experimentations. Here I have listed the problems that were posed by Rutherford model that did not explain the atom, that its negatively charged electrons are located in space that is surrounding the nucleus, why they are there. It does not explain why they don't fall to the center, why the electrons are not making sure to collapse the atom. Atom is there. It is for billions of years there. Why it is not showing any attraction towards the nucleus? What prevents the negatively charged electrons to be drawn into the positive charge? And there is no explanation of the spectrum of atom, the discrete spectrums that are there. The electromagnetic theory says electrons that are moving around, when they are revolving around a center, they are moving in a circular path, they must give off energy, and then they will continuously fall, and they will fall, and they will destroy the atom. Atoms I have shown to have the discrete spectrums when they are heated. And everybody knows when the, in chemistry experiments, when a particular mixture or a compound or a element, pure form elements are heated, they emit light, and that emitted light is in the discrete form. This discrete spectrums were measured and also categorized, and the catalogs were made, and they are there. So Rutherford model is not telling the complete story. Classical physics is a very meaningful physics, but it fails to provide any analysis of atomic structures because of the pure particle or pure wave nature. So we had to go further to address such problems. And the Bohr's atomic model combines both the classical and the modern thoughts and the ideas that the waves and the particles ideology can coexist. The wave and particle duality can exist. A particle can be wave, a wave can be particle. And such an explanation will provide a good atomic model. But first we need to understand why wave-particle duality is there. Is it real or hypothetical? Is this real for the microscopic particles? Is this real for the macroscopic particles? Where to go with this duality? So Bohr's atomic model emerged after the verifications of the wave-particle duality, and it started combining the classical and the modern ideas together, and the birth of the quantum mechanics took place. the quantum mechanical ideas have a basis with this ideology that the waves and the particles coexist. A particle can exhibit a face of wave, and a wave can have a face of a particle. The properties are interchangeable, and realization is interchangeable, and therefore usefulness is interchangeable, but it happens at only microscopic level. At macroscopic level, it becomes immaterial. And so there are limits. So there are approaches. When we narrow down certain variables, then we come to know that the wave-particle duality is a valid thing, and it is a good reason and a good argument with which we can move further. And we can give up the classical idea of a particle-only notion for the atomic structures. Here we have assumed that the nucleus is a hard particle, and we have assumed that the electrons are hard particles that are revolving around. As soon as we convert them into waves, and those waves that are stationary waves, then another model will tell the complete story. It must combine the both ideas that the most of the atom is empty, and it has electrons revolving around the nucleus, however, in the form of stationary waves. The atom has particles and waves. So, up to this point, what we know about the atom. Small dense matter, positively charged, called nucleus at the center. Small light with very, very small mass, negatively charged, subcomponents that are circling around the nucleus, termed as electrons. And later on, we had addition of neutrons, that the nucleus has neutrons inside, and we should be able to explain using new model where the electrons are located, why the atoms are stable, and we should be able to explain the energy emitted and the absorbed, and the spectrum, and the complete spectrum story. Then the model will be a believable model. Thank you so much.